So chapter 3, luckily it's a nice easy section to begin with. We're going to start working with quadratic functions and their models. So we're looking at quadratic functions using the standard form, also known as the vertex form. We'll look at maximums and minimums of these quadratic functions, and then looking at some modeling with functions. Okay, so this is the standard expansion of a polynomial, right? Hopefully you've seen this before. So this is just the definition of a polynomial of degree n. So here we have x to the nth power, x to the 7th power, right? So this is just the standard one. All the a's are constants. So for example, this could be used to express p of x, p of x equal to, I don't know, 7x to the 6th power plus 2x to the 4th power minus 8x plus 2, right? So here's a polynomial of degree n equals to 6, and this guy right here would be a sub 6. A sub 6 as its notation would be equal to 7 as a subscript, right? So that's this constant. This is the case where n equals to 6. N equals to 6. And then there's this sort of countdown that happens, power of 6, so then there's a power of 5, power of 4, power of 3. If they're not there, like in this case, there is no power of x equals to 6, then what you can think of is putting an extra term there with a 0 in front. Right? I can squeeze this right in here, plus 0 times x to the 5th plus 2x to the 4th, and then I can put plus, over here I can put a plus x to the 3rd power with a 0 in front as well, and plus 0 x to the 2nd power. And then squeeze that right in here, and then I'd have the whole polynomial expanded down. Does that make sense? Got kind of messy, so maybe I should write it over here. X to the 6th plus 0x to the 5th plus 2x to the 4th plus 0x to the 3rd plus 0 x to the 2nd minus 8x plus 2. Okay, so then what we've done now is written it into this sort of polynomial form where a sub 6 is a 7, a sub 5 is a 0, a sub 4 is a 2, right, and so on and so forth. A sub naught, or a sub 0, this one, is a 2, which is the constant of our polynomial. Any questions about this sort of expansion of polynomials? Okay. Well, if we consider the case where we just have a degree 1 polynomial or a degree 0 polynomial, then we have constants, an equation where the polynomial equals a constant, or the case where a polynomial equals a linear equation. Good. So here is a polynomial of degree 0 is this one, right? So there is no x to the 0 power. So degree 0, and it's just a constant. This is just going to be horizontal lines. Right? An example of a polynomial of degree 0 would just be the case, the polynomial p of x equals, I don't know, about 2. P of x equals 2, which is the same thing as just the function y equals to 2. Sorry, that function is equivalent to just saying the line y equals to 2, which is a horizontal line, right? So all of these are going to be horizontal lines. Whereas if we look at polynomials of degree 1, well, all of these are linear equations, where this is going to be the slope, and then 0 comma a sub naught is the y-intercept. Any questions? No? No? Okay, so we've done a lot of work with degree 0 polynomials, degree 1 polynomials. So this section is going to be focusing on degree 2 polynomials. So a degree 2 polynomial is also called a quadratic. So a degree 2 polynomial is going to be the case where we expand our polynomial out to degree 2, And so therefore the a is not allowed to be 0, right? The constant in front is not allowed to be 0. These are really popular, and often we change the notation over back to having a, b, and c be constants. And I don't know if that's a source of confusion, but sometimes is, right? So we just a second ago had this written down as a sub 2 x to the second power plus a sub 1 x to the first power plus a sub naught. So in this style of notation, here the constant associated with the x squared is a sub 2. This constant becomes a sub 1, and this constant becomes a sub naught. But either way, you're expressing the same thing. I don't know if it's better to switch over to ABC rather than to leave it into the in this format with little subscripts. I don't know, maybe it's a little smoother looking, and once we work with it and do, work through algebra with various equations, it might look a little bit more confusing. But we've already ran into the quadratic formula, for example, and the quadratic formula relies on this kind of format, A, B, C, right? The quadratic formula is negative b plus or minus root b squared minus 4ac all over 2a. So this formula is depending on exactly this. So I don't know if it would be more difficult for people to remember the formula this way. Negative a sub 1 plus or minus a sub 1 squared minus 4 times a sub 2 a sub 3 a sub naught a sub naught square root of that whole thing all over 2 times a sub 2. I don't know. Is this more difficult to remember? Probably. Gets a little confusing, I think. So anyway, we're just really used to ABC. But that should be the exact same thing as using a sub 2, a sub 1, a sub naught. Question?
Is there a benefit to using the subscripts later on or something?
I wouldn't. What would be the benefit? Well, the only real benefit is when you're speaking in abstract, like here, and expressing the whole thing. You want to express an nth degree polynomial, right? So if I wanted to express in general, in abstract, an nth degree polynomial, then, okay, so then we have that guy, and then we have a sub, okay, so this one's going to be minus 1, so like this could be 13, 12, and then the next one. But, what could we do to put the constants that go out in front? What could go there? Well, if I stick to the letters, first of all, I'm already using a there, so I don't skip the letter a or use a different letter. I don't know. Okay, well, I guess I could have used, sorry, I could have used x, not a. I like this. I meant to put it x here. X to the nth power, x to the n minus 1, x to the n minus 2. So what's the constant that goes there? Okay, well, we could use the standard ABC thing, A, B, C, D, but eventually we're going to run out of letters. So it gets to a point where there's so many of these, there's so many letters that it's really difficult to deal with them. And so typically beyond quadratics, we get away from the ABC, just because then D, then E, then F, maybe D. Sometimes I see 4 of them, A, B, C, D. But then A, B, C, D, E, F, A, B, C, D, E, F, G, H, like how many letters do I have to keep track of? So eventually, just for that sake, it becomes a little easier to deal with the subscripts than it is to deal with new letters. But that's sort of a style thing. Maybe some people prefer to deal with 9 different letters rather than the subscripts of 1, 2, 3, 4. This is, I think, a little easier to memorize and see the pattern. I can see why it might be a little harder to memorize a sub 1 there, a sub 1 there, a sub 2 there, a sub 0 there, a sub 2 there. Right? It's a little harder to come up with a little song to help you memorize this than it is to come up with a little song to memorize that, or a little, memory. Okay. Anyway, I think at this point I wouldn't worry too much about it. It's nice to at least begin to see it in general and in abstract. And as you go into calculus, you'll see as you read the proofs and the theorems and stuff, very often they use this kind of notation to represent an abstract polynomial or just abstract concepts. Good. But for now, we are going to go back to ABC for this style of notation for quadratics. Okay, moving on. Graphing quadratic functions using the standard form. Okay, so if we take x equals to 1, b and c equal to 0, then this whole thing just breaks down to just give you x squared, right? So in the special case where this guy happens to be the constant 0, and this guy happens to be the constant 0, and this guy happens to be the constant 1, then we have ourselves a x squared, right? Whose graph is the standard parabola that we're all very accustomed to seeing by now, right? Your standard parabola goes this way. Just as a rough idea, it has this sort of a shape, right? It goes this way and goes that way, but not as ugly. But the general shape of it looks like that. Goes through the origin, point 0, 0, and we can come up with a couple of other points on there that describe it, right? Okay, so now we're going to look at something called the standard form, or also known as the vertex form. The standard form of a quadratic looks like this. F of x equals to a, parentheses, x minus h, parentheses, to the power of 2 plus k, where this is equivalent to that, right? This is an important thing people confuse. These two things are equivalent to each other. We can always use algebra to go back and forth between them. There are some advantages to leaving an equation like this, and there are some advantages to rewriting it and making it fit this form. But algebra lets us go back and forth between these always, right? So you have that freedom to manipulate your equation whenever it's given this way, to rewrite it this way, or the other way around. When you start with this and you go this way, when you start with the standard form and you want to go to the polynomial form, super easy. All you have to do is FOIL this, right? You have something, a binomial squared. You just FOIL it all out, distribute the a, combine the k, and you're there. It's very easy. When you want to go in this direction, when you start off with a polynomial and you want to write it in standard form or vertex form, that could take a little bit of work. We use a process called completing the square to do that, and that could take a little bit more work. What's the advantage of these? Well, there are some advantages to both. In this, the main advantage of writing things in the standard form is that from the section on transformations, we can tell what this is, the rough sketch of this, because we know what happens to a function when we subtract a constant in the argument of the function. We know what happens to our function when we multiply by a constant, and we know what happens to a function when we add a constant. Good. All right, so let's review some of those things. So this is what's going to become useful. Let's say we have our function. Here's f of x equals to x squared. And again, we know that the standard graph for this thing is just your standard parabola that goes that way. But from our work with transformations, we know that if we just have a new function, say g of x, which is equal to f of x plus 2, what does this do? The fact that it's plus 2 is going to shift the whole thing up by 2 units, right? Like this. So it's going to be similar to that one, except it's going to be shifted up by 2 units. So that'll be the point 0, 2. And then we keep the same shape. That's what happens when we add a plus 2 there. Same thing when we subtract a constant, it means that we bring it down. On the other hand, if we have a new function, h of x, which is very similar to the old function, except that we're going to evaluate it at x minus 2, we know that if we replace the x with an x minus 2, this is a horizontal shift. Right? This means that the original graph gets shifted, and it's a little counterintuitive. You'd think minus 2 you'd go this way, but it's the other way around. Think about where the new 0 is. The old 0 used to be at 0, 0 here, but a new 0 occurs when x equals to positive 2. So this graph gets shifted this way, like this. So it's a standard parabola, but it's been shifted to the right by 2 units. So this is the point 2, 0. Good. And likewise, we know what happens when we multiply by a constant. So if we have a new function, which is equal to, say, 4 times f of x, then we know that that 4 makes it go toward infinity faster. So it's going to be similar to this function, only a lot skinnier. Right? So if the original one is this one, this is the original f of x, then this new function is going to be much skinnier because we're multiplying everything by 4. So it's going to go toward infinity faster. And what happens when we multiply the function by a negative one? We multiply the function on the outside by negative 1, it's going to be a reflection about the x-axis. And so let's say, again, we have a new function, I don't know, p of x, which is equal to negative 1 times f of x. Then this is going to be similar to our parabola, but upside down. The negative 1 is a reflection about the x-axis. Good. Any questions about these things? No? Okay, so armed with that knowledge, when we're looking at this function, if we know f of x is a quadratic, we know that the standard graph of f of x, well, the standard graph of a parabola x squared is it's a parabola centered at the origin. Then we know that the k here impacts it by shifting the whole thing up and down, whether k is positive or negative. We know that the h will be a horizontal shift, left and right. We shifted left and right by h. And we know that the constant out here will affect it by making either skinnier or wider. Good. Okay. Now I did some ugly little graphs here to kind of demonstrate that, but we can also use Desmos. Desmos. Okay, so we have our function f of x equals to x to the power of 2. Here's our standard parabola. Let's leave it in blue. Okay, so here's our standard x squared. And now if we have a new polynomial, h of x, which is equal to f of x plus 2. Let's put it in red. Let's put it in red. There. So putting a plus 2 shifts the whole thing up by 2 units. By 2 units. I can also shift it by 4 and shifts it up by 2 units. I can put it up by 10 and it'll shift it up 10 units. I can also subtract minus 2. It'll shift it down, or minus 7. It'll shift it even further down. Good. So adding or subtracting a constant there shifts it up and down. So I can add the constant plus k and then turn that into a little slider. And then that way the equation changes here. Let's put the equation. How about at 10, 10, 5. And let's put label, and I want to put x to the second power, or f of x. I don't see that. I'll put y. We'll go back to the y equals notation. Y equals, and then plus $sign squiggly k. Squiggly. Maybe that doesn't. And then let's put this in parentheses. And let's make this large. And that looks good. Okay, so okay, so here is the original function in blue is the, let's change this to red to match. So the original function in blue is x squared, and then here is this this function here, and we can see what happens when we add or subtract a constant. Right, so the red one right there is x squared minus 2.2. The red one there is x squared plus 5.2. Okay, so I hope that that part's clear. Okay, so what happens when we add or subtract a constant in the argument of the function? So let's get rid of that guy and do a new function, g w of x equals 2, and then I can do fx minus 2. So putting a minus 2 in the argument of the function here gives you minus x minus 2 squared, and then that would be this black one right in here. Again, I can just move it around and say, well, I don't want a minus 2. I could do a minus 4, and it shifts it all the way to 4. I could do a minus 8, shifts it all the way over there. I can also do a plus 2, and it shifts it to the left. So it's a little counterintuitive that the plus moves it over there, but think about where the new 0 is. X equals to negative 2 is going to give you my new 0. Okay, so again, I can leave it as a slider. So let's leave it as a minus h, where h is going to be a slider. Now, why do I have a problem here? Is it because this thing is labeled as a thing? What do I want to do? Good. Okay, so that fixed it. So now I have H as my slider, and I can do another label at, say, 10. Okay, so here we have an equation of x minus 1 squared, and then I can move it around. So that's x minus 2.5 squared. And then, oh, well, there'd be a minus minus situation here, so that would make it a plus. So let's put an extra parenthesis in here. So when we go, whoops, didn't like that. So hopefully it's clear that if we put it into this format, the plus or minus inside the argument of the function shifts it left and right. And then finally, the last one we want to look at is multiplying by a constant. So if we had a new function, and let's see, we tried p, w, we want to use and we're making that one a green one. Okay, and so if we had, say, this, right, multiplying the original function by a 3 makes every value get tripled. The output of every value of f of x gets tripled. So you go toward infinity faster, the graph ends up looking skinnier. The bigger that constant is, the skinnier it's going to be. Okay. On the other hand, if you multiply by a fraction between 0 and 1, it slows down the growth. So multiplying it by 0.8 is going to make it a little wider. Multiplying it by 0.5 is going to make it a little wider. Multiplying it by 0.4, 0.2, say, makes it even wider. Right, all the way out to 0. If you multiply by 0, then it's just going to be the horizontal line that is the x-axis. If you multiply by a negative, -1, it's going to be a reflection about the x-axis. It makes all the outputs negative, so it just flips it upside down like that. And the same idea grows that if you multiply by a negative that's bigger than 1, like -5, it's going to be skinnier and flipped upside down. -8, even skinnier, flipped upside down. Or if you multiply by -0.5, it's going to make it wider and upside down. So it's just sort of a combination of all those things. So again, I can just make it some constant a times f of x. And let's change these parameters a little bit. Let's just make it -5 to +5, 5.1. See if that'll work. Okay, so here we have it going, becoming a constant. Oh, let's label it. I don't know how to. Just y equals a constant squiggly, and then x to the power of 2, and then this way, and then okay, so there we go. So here's the equation: x squared multiplied by 2.5, x squared multiplied by 2.9, x squared multiplied by 3.8. Right. So the bigger the number, the skinnier it gets. And then if we multiply by a number between 0 and 1, it just gets a little wider, 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 wider until we get to 0. And then negative, wide, but negative upside down, and then goes this way. Okay, so those are the 3 things we want to play with. Left and right, upside, make it wider and skinnier, move it left and right, or move it upside, up and down. And then, of course, we can combine all 3 of those things. And let's do one last one. Where do I use G? Use G, how do I? G of x equals to the constant a, f times x minus h plus k. So now we have 3 levers to pull from. Okay, so we have our 3 levers. The constant on front makes it skinnier, 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 wider, 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 or flips it upside down. The k moves it left, up and down. Right, I'm looking at this equation here. Maybe I should put that next to it too. Let's just, there's a lot of mess stuff going on here. I don't need any of this. I don't need any of this. I don't need that anymore. Still using that. I don't need that one anymore. Okay, so here's our standard equation. The a out in front of the f moves it by, affects it by making it skinnier or wider or upside down. The k moves it up and down, and the h moves it left and right. Okay. Now, keeping track of where the vertex is, if I have this as the original vertex of 0, 0, and then I have a new function that fits this format, the k moved it up and down. And let's get back to making a equal to 1. A equal to 1. The k, 1. The k equal to 0. And the h equal to 0. So the k moves it up and down. So the original vertex is going to be affected by the k. So if I move it there, it'll be 0, comma k that belongs there. And then the h affects it by moving it left and right. So the x coordinate is affected by the value of h. Okay, so point being that h comma k becomes the vertex of this equation. Right, notice that right now here's the vertex, and here's the equation. X minus 3.1 to the second power plus 2.9. And if I move this way, move this way, then here is this equation. X minus 3.1 and then plus negative 2.7, and then here becomes the new vertex. Okay, any questions about this? No? No? Good, good, good. Okay, so back to this guy. So here is, again, the equation in vertex form, where h comma k is the new vertex. Good. Where if a is positive, it opens up like a happy face, right? So if the leading constant here, a, is positive, it opens up like a happy face. If the leading constant is negative, then it opens down like a sad face. Constant is negative, upside down like a sad face. Constant is positive, it opens up. Good. Okay, armed with that, let's figure out a way to do this. Let's express this in the vertex form. How do we do that? Well, that's hard work. To do that, we're going to have to do a process called completing the square, which we've done before, but let's practice it. So 2x squared, 12, and 23. Equals to 2x squared, what is it? Minus 12 minus 12x plus 23. Okay. All right, so what we want to do, the first thing we want to do is factor out whatever constant is in front of the x squared. We need that to be a 1. So step number 1 is going to be to factor out that 2. 2 parentheses x squared minus, okay, that turns into a 6 plus 23. Now, you don't have to factor out that last constant since it's an even number, so it doesn't really matter. Okay, so now we're going to focus our work on just this part inside here, inside the parentheses. We're going to complete the square. Remember, the process for completing the square was to add and subtract the perfect thing, the perfect number to make it a perfect square trinomial. And the formula for that is to do half this number and square it. So this number times a half, and then square the whole thing. That's the formula for completing the square. So that will be negative 3 squared, which gives you a 9. So 9 is the perfect value to add and subtract to this. So f of x is equal to f of x equals to 2 parentheses x squared minus 6x plus 9 minus 9. Since adding and subtracting the same thing doesn't change the equation, I've added a 0. Okay, and now that guarantees that these three terms are going to be a perfect square trinomial. And it might be easy to spot and recognize it with nice, easy numbers. But the pattern is that it's equal to x minus, and then whatever this was before you squared it. X minus 3 squared. Right, so x minus 3, and I know it's a minus 3 because this used to be a minus. And then I can verify it if I want to. If I FOIL this out, I know I'm going to get these three terms. There's still a minus 9 from here, parentheses, there's still a 2 out here, and there's still a 23 out here. Good. Now we just distribute that 2 and combine like terms, and we'll be done. So it'll be 2 x minus 3 squared. Now be careful because that 2 on the outside applies to the 9. So we're going to have to distribute. This guy goes into here, but this guy also multiplies by that. So we'll have a minus 18. minus 18 plus 23. Good. And so finally, we combine these last two to give me a positive 5. Good. Okay, so this fits the vertex form, the standard vertex form of a quadratic, where the A is being played, the role of A is being played by a 2. The role of H is being played by this 3. And the role of K, the constant, is being played by this 5. Good. Good. So if we try and graph it, right, let's try and use Desmos to confirm that everything works out the way we think it does. So let's graph the original one. 2x to the power of 2 minus 12x plus 23. So there's the original graph right here. Zoom out a little bit more. Here's the original one, written like this: 2x squared minus 12x plus 23. And now that we've done our work to convert it into the vertex form, we have a new equation. H equals to 2 parentheses x minus 3 to the power of 3, sorry, power of 2, plus 5. And let's put it in red. And it's the same equation, right? So here's the original one in blue, here's the new one in red. So they're the exact same graph, right? So that confirms that this is equivalent to that. They both give you the same graphs. And if we look at the vertex, right in here, the vertex of it is 3, 5, which is this, 3, 5. So there's the first advantage to converting this into this. We get a nice rough sketch of what it looks like. We know that it's going to be a parabola that's a little skinnier than normal because of this 2. It opens up like a happy face because this is positive. It shifts to the right by 3 units because of this minus 3. And it shifts up by 5 units because of this 5. The vertex is 3, 5. And knowing that it's a quadratic, knowing the rough sketch, knowing what the vertex is, solves a lot of different word problems. There's a lot of different word problems where you're interested in figuring this out, what the vertex is. Any questions? No? Okay, well, this is what the author did. They did it in a similar way. It's a little bit different. They factored out the 2. Now, I like to do the plus 9 and minus 9 both inside the parentheses, but I know that some people like to do it this way. They just attach it to the end here, but keeping in mind that they're really multiplying by 2, so they kind of do that in a slightly different order. It's up to you, however you learn to do it. Either way is fine. Either way, we get to the same answer. Okay. Once we have it in the into this standard vertex form, then as we saw, we can do a pretty good rough sketch of how to graph it. And if we go back to the original standard polynomial form, we can find when this function equals to 0. We can set it equal to 0 and solve for these. Now, why is this, from the standard form of f, we can see that the vertex of f is equal to this, with y-intercept equal to 13. To find the x-intercepts, what am I looking at? Something is wrong here. Ah, there's a mistake. So there's a little mistake here that the author made. I was like wondering what's happening here. So to find the x-intercepts, we set it equal to 0, right? We figure out when the output is 0, so this step is right. But then notice that that means that this is the A, this is the B, and this is the C. Right? This is A, B, and C. But then right here they made a little mistake. They put a 13 instead of a 23. Okay, so that's why they end up getting real number solutions when we know that the answer should be imaginary. And how do I know right off the bat that the answer should be imaginary? Because I already know the graph. The graph goes this way. It never crosses the x-axis, so I know that the x-intercept points are imaginary values. Good? You caught that? Yeah? So there should be a 23 here, which means we'll have 23 times 8. 144 minus 23 times 8 is going to be a negative number, and so we'll end up getting 2 imaginary solutions. Good. Wait, again, did I do something weird? Did they get a different thing? Why do I keep getting... plus 23. Oh, okay, they made a mistake all the way over here. Okay, so this author is all the way, way off over here. So this is 23 minus 18. It should have been plus 5, not minus 5. Sorry, should have caught that. So the author was off a little bit. And then they made a mistake here. Okay, well, there's just mistakes everywhere. Let's just move on. The domain. Oh, what is the domain? The domain of this parabola is all real numbers. And the range is going to be starting at a height of 5, right? So from 5 to positive infinity will be our range. So let's go back over here. So the domain of this function is all real numbers. But the range is starting at 5 going out to infinity. Good. Questions? Good. The maximums and minimum values of a quadratic function. Okay, so as we saw, the vertex is really important. When the parabola opens up like this, concave up is the word for it, concave up, then the vertex is the minimum value experienced. When the parabola opens down this way, concave down, then the vertex is the maximum value. So there'll be lots of word problems and lots of situations where finding the vertex is important. It's a unique part of the graph that might represent the maximum profit, for example, or minimum loss, or minimum risk, or just a variety of different applications. So we're always interested in figuring that out. Okay, consider this quadratic equation, express it in standard form, and sketch the graph, find the minimum value. Okay, so again, another opportunity to practice our complete the square process. So let's add a slide. So 5x squared minus 30x plus 49. Okay, so factor out that 5. We'll get x squared minus 6x plus 49. And then we want to add and subtract the perfect thing. That's going to be half of this squared. Same as before, we're going to end up with 1/2 of the negative 6 squared gives you negative 3 squared equals to 9. Okay, so then that's what we add and subtract. We get 5 you guys hear that siren? In movies, this is where you also hear the siren and realize we're neighbors. All right, so plus 9 minus 9, right? And then plus 49 still out here. Now we know that the first three are perfect square trinomials. It's going to give us an x minus 3 squared. Still a minus 9. There's still a 5 out here. And there's still a plus 49 out here. Okay, then we distribute this 5. This 5 gets distributed onto here. This 5 gets distributed onto here. And so we end up with 5 x minus 3 minus 3 squared minus 45 plus 4. Plus 49. So the whole thing is going to be plus 4. 5x minus 3 squared plus 4. Good. Okay, so this fits the form where the a equals to 5, the h equals to 3, and the h and the k equals to 4. Good. So I know it's going to be skinnier than normal by a factor of 5. It's going to go toward infinity faster, so compared to the standard parabola, skinnier. Compared to the standard parabola, shifted to the right by 3 units, and shifted up by 4 units, where this is the vertex, 3, 4. Right? So if we were asked to do a rough sketch by hand, all you have to do is just put something like this. And we know that this is going to be the point 3, 3, 4. Oh, come on. 3, 4. And then typically if you just put at least one more point on that parabola, it'll help people identify it as sort of the rough sketch. So try putting in one more point, and you can choose x to be any value at all, but why not let it be something that's easy to work with? How about a 2? If we let x equal to 2, we'll end up with a 1 squared, which is going to be equal to 1 times 5 is 5, plus 4 is going to be 9. 2 leads to 5 times 2 minus 3 squared plus 4. Okay, that's going to be equal to 9. Okay, so you can just put another dot over here and say that this is the dot 2, 9. Any questions? No? No? Okay, so we got, we wrote it into the vertex form of a quadratic. We found the vertex of it. And then the other part of this question was sketch it, graph it, and then what's the minimum value? Well, the minimum value is the vertex. Right? So the minimum value is 3, 4. Notice that there is no maximum value in this case because it goes up. So it just keeps growing up to infinity. So unless they restrict some domain, they might say, what is the maximum value on a certain domain? Maybe they might give you a domain value of, I don't know, from 1 through 9. Oops, 1 through, come on, say 5. From 1 through 5, what's the maximum value? Okay, they could give you that. But if they don't restrict the domain, then there is no maximum value. Right? But there is a minimum value. The minimum value is the vertex because it opens up. Any questions? See if the author did this right this time. Factor out of 5, factor it, we get that, we get a plus 9, I mean a plus 4, there we go. Opens up this way, good. Another good place for us to be able to identify a point is the y-axis, the y-intercept point. And that one's easy to get because all you have to do is submit a 0. If we submit a 0 here, we end up with negative 3 squared, which is 9. 9 times 5 is 45, plus 4 makes it 49. So that makes it easy. But also, remember, we were originally given this equation in the standard polynomial form, and we know that if we let x equal to 0 here and here, this is the y-intercept point. So really, we could have gotten that point without really doing much work at all. Okay, so that's why we know that this is the point 0, 49. We also found another point at 1, 2, 2, 9. So it doesn't matter, just a couple of points. Any questions? Good. One more time, similar. Just going to practice doing the quadratic formula, converting it into the vertex form one more time. So we have negative x squared plus x, and I think it was plus 2. Plus 2. It's more of the same. Convert it into the vertex form of a quadratic so we can figure out the minimum and the maximum. Okay, so the first thing we have to do is factor out this minus 1. And now we have an x squared minus x. And then there's still a plus 2 out here. And remember, the little formula for the perfect thing to add or subtract is going to be half of this squared. So it's going to be 1/2 times negative 1 squared. Well, that's going to be negative 1/2 squared. Which equals to positive 1/4. Good. Okay, so then we're going to add and subtract that. Equals this. equals negative 1 times x squared minus x plus 1/4 minus 1/4. Okay. Now we know that the first three are going to be a perfect square trinomial. And if it's not super clear what it's supposed to be, remember the pattern is that it's equal to this thing before we square it. So I know that it's going to be x minus a half squared. Not sure, you can FOIL this out to confirm it, and you will get this term in here. There's still a 1/4 out here. There's still a minus 1 out here. And there's still a plus 2 out here. Okay, so now we have to distribute this and distribute that. And we get minus x minus 1/2 squared. Come on. Squared plus 1/4 plus 2. Good. Common denominator is going to be 4, so we put a little 1 underneath here. Put a little 1 underneath here. Multiply it by 4/4. And I end up with 8. 8 plus 1 is 9. 9/4. So this equals to negative x minus 1/2 squared plus 9/4. That was nothing. Okay, so what's it going to be? Compared to the standard parabola, I know that it's going to be flipped upside down because there's a minus here, so it's going to open down. That means that the vertex is going to be the maximum point, and the vertex is going to happen at the point 1/2 comma 9/4, 9/4, or 2 1/4. Good. Questions, questions, questions? I know that the y-intercept is 0, 2. So I can do a rough sketch of this thing. It goes to the point 0, 2. Let's say this is 0, 2. And I know that it's got a vertex point of 1/2 comma 2. Okay, so it's going to be like up here somewhere. The scaling is a little off, but we're okay. 1/2 comma 9/4. Okay, so this is going to curve down this way and down this way, right? Where this is the vertex, and it will also be the max. Answer everything, sketch the graph, find the max. Okay. Let's see if they got the same result. Yep, they got the same result I did as well. Factor out the minus, add the perfect value, combine, simplify, and get to our answer. Any questions? Here's a sketch of it. A little better than mine, but similar. And it goes to the point 0, 2, the y-intercept. Coefficient of x squared is negative. F of x has a maximum at that point. Expressing a quadratic function in standard form helps us to sketch the graph as well as to find the maximum and minimum value. If we're interested in only finding the maximum and minimum value, then a formula is available to do so. And in order to find that formula, what we have to do is apply the complete the square process to this in general. So if we solve this in general and try to do complete the square process, we'll end up with this guy, right? We're going to add and subtract the perfect thing. We're going to combine things. We're going to get, right? So I'm not going to go through the details of this. It's in your book, so you can look at it if you'd like. But the point is that if we apply the complete square process to that formula in general, and maybe this should have been in the same screen here. So this is starting with ax squared plus bx plus c. right? The first thing we do is we factor out whatever's in front of the x squared in order to make sure there's a 1 there. That's why we factor out the a. And so we get these. And then we add and subtract the perfect thing. Remember, the perfect thing is the constant in front of the x. We multiply it by a half and square it. That's how they get this. Add this. Now I add and subtracted. The author here does it a little bit different. So that's why there's this minus term over here. And then you simplify, combine things, and you end up with this, where this is the h term, and then these two are the k term. This is the h, negative this is the h, if we have a minus here. Well, I shouldn't, yeah. So in comparison to the a x minus h squared plus k, this whole thing here is k. So what we want to draw attention to is that the x coordinate of our vertex is equal to this guy right here. And that's really the formula we're going to use. Okay? So this is the x coordinate of the vertex, negative b over 2a. Right? Given a polynomial that fits this form, if you want to find the vertex, well, we can very easily find the x coordinate. Now the y coordinate of the vertex is this, and you could use this formula, c minus b squared over 4a, and that will give you the result. But it's just easier to just evaluate the original function at the x coordinate and get your result that way. For example, let's say, I know this might look a little confusing, let's say that you are given the quadratic, you're given the quadratic equation f of x equals 3x squared plus 4x plus 5. I don't know, something like that. And you're trying to find the vertex of this thing. Okay, well, we could go through the whole process to complete the square on all this and rewrite it into this format. But if we do it in general, we already have a formula for it. So I know that the vertex is going to be equal to this. The vertex equals the negative b over twice a, comma, and then this is the y-coordinate of the vertex, c minus b squared over 4a. This is the vertex. Well, if you want to memorize this formula, that's fine. But this thing is just a little bit more complicated to figure out. And it's just not the traditional way in which we ask people to do this work. What we normally ask people to do is to figure out this one, which is pretty easy, negative b over twice a. And then once you get an answer to that, then to get the y output, then they ask you to evaluate that function at that point. Evaluate it at negative b over twice a. Twice a. Okay, let's look at an example. Find the maximum limit value of each of these quadratic formulas. Okay, so in order to find the vertex, I need to figure out the formula. So we're going to let the x coordinate of vertex is given by the formula negative b over twice a, where this a and b is referring to ax squared plus bx plus c. So in this first equation, the a is a 1, and the b equals a 4. Okay. So for this first one, we get negative 4 over 2 times 1, which equals to negative 2. So the x-coordinate of the vertex is negative 2. Now to find the y-coordinate, we could go to that other formula, c minus b squared over 4a, and plug that all in here. C minus, okay. And remember, if there is no c here, that means that there's a plus 0. So for us, the c is a 0. Okay. Or the other thing we could do is evaluate this polynomial at negative 2. The y-coordinate of the vertex is equal to f of negative 2. Which is equal to negative 2 squared, negative 2 squared, plus 4 times negative 2. So that's going to be 4 plus negative 8 gives you negative 4. Okay. So my vertex is going to be negative 2 comma negative 4. Questions? The constant in front, a equals to 1, is positive. So I know that this parabola opens up. And because it opens up, that must mean that this is a minimum. It's the vertex. And it's also the minimum. Right? Because the parabola opens up. This one opens down. I already know that because this guy is negative. So whatever the vertex is going to be, I know the vertex is going to be a maximum value. Man, this computer is just struggling. B is a 4. And C is a negative 5. Good. So the x coordinate of the vertex is going to be equal to negative 4 divided by 2 times negative 2. Gives me negative 4 over negative 4. It's just going to be equal to positive 1. Good. And so now the y coordinate is going to be to evaluate that function at positive 1. So it would be g of 1 which equals to negative 2 squared plus 4 times something minus 5. And then this becomes 1 and 1, which gets me to negative 2 plus 4 gets me to 2. 2 minus 3 is negative 3. So I have the ordered pair 1, comma, negative 3. And I know that that's both the vertex as well as the maximum value.